This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 9 of Week 2. Drag and viscous flow, Reynolds number, drag coefficient, boundary layers, and the drag crisis. The Handbook gives fluid properties and Reynolds. The drag coefficient tables come from Sengel and White. Drag on any body lives inside one equation. F sub d equals 1/2 c sub d times rho times v squared times a. The drag coefficient is a function of one dimensionless parameter, the Reynolds number. Two regimes matter: high Reynolds, pressure drag from a separated wake, c sub d roughly constant for each shape. Low Reynolds, Stokes flow, drag purely viscous, linear in velocity. The drag coefficient tables aren't in the Handbook. They live in Sengel and White. Reynolds number is the ratio of inertial to viscous forces, rho Vd over mu, or Vd over nu, with nu the kinematic viscosity. Use diameter for a sphere, distance from the leading edge for a flat plate. When Reynolds is large, viscous effects squeeze into a thin boundary layer, and the flow separates behind Bluff bodies. The wake drives the drag. When Reynolds is small, viscosity fills the field, and there's no wake. 3 keyword signatures. 1. Sphere of diameter d through air or water at velocity v. High Reynolds drag, standard equation. 2. Terminal or settling velocity, set drag equal to weight minus buoyancy. Verify Reynolds afterward. 3. Flow over a flat plate, boundary layer thickness at distance x. Check the local Reynolds against 5 times 10 to the 5th. First move on every stem, write Reynolds. It picks the regime, which picks the formula. Variable table for drag. Density and viscosity from the property tables, velocity, diameter, and area from the geometry. Compute Reynolds, that fixes the regime. Then look up C sub d for the shape from a Sengel or White table. Compute the dynamic pressure, multiply by C sub d and frontal area, and you have the drag force. The table forces you to write Reynolds before you grab a coefficient. The C sub d versus Reynolds curve for a smooth sphere is the most asked drag diagram. Pull it from Sengel or White. 5 regions. Stokes flow below Reynolds 1. C sub d equals 24 over Reynolds, a straight line on log paper. Intermediate, 1 to about 1,000. The curve drops smoothly. Subcritical, 1,000 to 3 times 10 to the 5th. C sub d flat, near 0.47. The drag crisis at 3 times 10 to the 5th. C sub d plunges to about 0.1 as the boundary layer goes turbulent and the wake narrows. Supercritical above that. C sub d drifts slowly back up. Worked problem. A smooth sphere, diameter 0.3 meters, through still air at 30 meters per second. C sub d is given as 0.47 from the Sengel sphere table. Air density 1.225. Find the drag force in newtons. 3 steps. Frontal area, pi d squared over 4. Dynamic pressure, 1/2 rho v squared. Don't drop the 1/2. Then drag is C sub d times dynamic pressure times frontal area. About 18.3 newtons. About 18.3 newtons. Verify the C sub d assumption. Reynolds is Vd over nu, 6 times 10 to the 5th, just past the drag crisis. The exam usually gives C sub d, or pins Reynolds, in the flat subcritical plateau. Variation. Terminal velocity of a falling hailstone, 20 mm diameter, density 900, in air. Drag equals weight minus buoyancy. The closed form is the square root of 4gd times the density difference over 3 C sub d rho fluid, about 20.2. Reynolds checks at 2.7 times 10 to the 4th, comfortably subcritical. So C sub d, 0.47, holds. Stokes regime variation. Tiny sphere, 0.5 millimeter, settling at 5 millimeters per second in oil. Reynolds is 0.022, far less than 1, so Stokes flow applies. Stokes drag has no 1/2 rho v squared. It's purely viscous, 3 pi mu Vd, about 2.36 micronewtons. Sengel and White listed directly. Boundary layer variation. Air over a flat plate at 8 meters per second. Find delta at x of 0.5. Local Reynolds is 2.67 times 10 to the fifth, below the 5 times 10 to the fifth transition, so the layer is laminar. Blasius gives delta as 5.0 times x divided by the square root of Reynolds, about 4.8 millimeters. Above transition, the turbulent power law, delta over x roughly 0.37 over Reynolds to the 1/5, both from Sengel and White. Reference C sub d values at high Reynolds, all from Chengel and White. A streamlined airfoil body near 0.04, flow stays attached, drag almost all friction. A smooth sphere, about 0.47, separation near the equator. A long cylinder near 1. A cube just above 1. A flat plate perpendicular to the flow, about 1.9, the worst case. 2 orders of magnitude separate airfoil from flat plate. Streamlining delays separation, shrinks the wake, collapses pressure drag. 5 traps. 1. Using C sub d 0.47 on a sphere at Reynolds below 1. In Stokes flow, it's 24 over Reynolds. 2. Confusing drag coefficient with skin friction coefficient, different reference areas. 3. Dropping the 1/2 from dynamic pressure, doubles the answer. 4. Using the full sphere surface area instead of the frontal projected area, quadruples the answer. 5. Substituting dynamic viscosity where kinematic belongs, without the density factor, throws Reynolds off by orders of magnitude. Take 6 things into the exam. Drag equals 1/2 C sub d times rho times v squared times frontal area. Never drop the 1/2. Reynolds picks the regime. The C sub d shape table comes from Sengel and White, not the handbook. Stokes drag is 3 pi mu Vd, valid only when Reynolds is much less than 1. Flat plate boundary layers transition near Reynolds sub x of 5 times 10 to the fifth. The smooth sphere drag crisis near 3 times 10 to the fifth. Fluid properties are in the handbook tables. Onward to topic 10, compressible flow, Mach number, and choked nozzles.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.